Alright, so it's finally time to look at how these inductors are taken into consideration in an electric circuit. Alright, so what we have here is a very simple electric circuit with a voltage source denoted by epsilon, and that supplies a current that'll pass through that switch and then across what is the inductor right there. So it's known as, well, a capital L, that's its variable, and the symbol is this squiggly, curly, loop-like thing. It looks like a little solenoid, right? And then the current will pass across the resistor, which you've seen before, and back into the battery. Okay, so that's basically a solenoid like we've talked about earlier, which means that as the current from the battery is passing through it this direction, it will induce a countercurrent of sorts this direction, right? Trying to oppose the increase in magnetic flux. There's a magnetic flux from the current from the battery as that goes around this circuit, right? That generates a magnetic field. Let's see, that'd be magnetic field inside the solenoid that direction. And so that flux will increase when the switch is closed over time, right? It'll increase up to a maximum amount, right? But in the meantime, it'll increase. And so the inductor works just like solenoids in that there's a countercurrent that way, there's a induced magnetic field up in this case to try and inhibit that increase in magnetic flux. Okay, so let's see how that inductor, right, L, relates to that EMF. To start, we have that the magnetic field, in general, is related to the current directly, right? And we know this from Biot-Savart, written like that, okay? We also know that the magnetic flux is directly related to the magnetic field, like this, right? Thus, if you take the first equation and plug it into the second, you get that the magnetic flux is directly related to the current. And we do that very simply by writing that, L times I, right? Where L is the inductance, and it's everything in this equation and that equation except for the current. In other words, it's constants like mu naught and 4 pi, and then it's quantities that are dependent upon the geometry of the inductor. For instance, the path length, say the radius of the inductor, and the cross-sectional area that the current will pass through, right? So all of those are dependent upon how the inductor is physically made. And so that's all thrown into one variable called L, which is the inductance of the inductor. And that's multiplied by the current, and that's another way to write the magnetic flux. Okay? This time, it's a lot more simple than the above equation. Okay? Let's see. You may be wondering why I didn't use Ampere's law to get B. Well, that's because Ampere's law is a very special case of Biot-Savart. It's special because you can only use Ampere's law when you have symmetry, right? Biot-Savart is helpful to define the magnetic field in any situation, for any geometry, whether you have symmetry or not. So that's why I went with Biot-Savart. All right, so if this is the magnetic flux equals the inductance times the current, the EMF is related to the flux by such, okay? Well, that means plugging in L times I, we can write it like this. Now I pull out the inductance because typically when an electric circuit is operating, right, the inductor isn't changing physical form or its physical characteristics. So the L has a constant value. So that can be pulled out. What does change is the current over time. So as soon as you close this switch, right, in all actuality, the current through the circuit does increase. Okay, does increase over time up to a maximum. We'll just say I max. Okay, so initially there's 0, and it does increase by a little bit. We'll see later exactly how. Right. So let's say that solenoid over here, or rather this inductor, has a total number of turns or loops, capital N. How do we change the EMF? Well, we simply multiply that by N. So minus NL di dt. All right, and that's that. That's the total EMF due to that inductor. And this is the term, right here, that we will use when evaluating inductors in series with resistors, right? In the next few videos, I have the cases of when we charge up an inductor, right? So when that switch is closed, we'll see what happens. We'll see what equation we can write out and how to solve it. And we'll see it when we have it charged up and then we discharge it from the battery. What happens? Is there still current? Is there not? Well, we'll see what happens and how to utilize this EMF term. Okay, so this is a way to relate the EMF to the actual inductance and the current.